What is a spill hole and how does it affect the flight of your rocket?
Welcome to Advanced Construction Videos, where we show you how to tackle rocketry, building techniques, and more. On our website, we sell kits, motors, building supplies, and electronics. So come and learn, shop, build, and fly when you visit us at apogeerockets.com.
Hi, I'm Tim Van Milligan from Apogee Components. We had a question recently from a customer asking about spill holes in parachutes. And the question was, how does it affect the descent rate of the parachute? So first of all, what is a spill hole? So a spill hole is you take a canopy on your parachute, like this plastic one here, and you can just take a knife and cut a circle in it. And often on our Apogee chutes, they have a nice circle that you can follow to cut a spill hole in your parachute, and that will end up something like this, where you can see there's a nice hole through the middle. Now, the purpose of the spill hole will do two things. One, because you have less surface area on your parachute, it is going to fall faster. And that's what his question was. But the second reason to cut a spill hole in your parachute is probably more important. That spill hole will help stabilize the parachute so that it doesn't oscillate so much as it's descending. Now, this is important when you have a delicate payload in your rocket. Say you're launching an egg up in the air and you want to get it down without cracking the egg. You don't want it swinging down back and forth as it's descending, because when it hits the ground, it's going to crack an egg. How do I know? Been there, done that. His question was, how does this spill hole affect the descent rate of the parachute? Well, for that, we're going to have to go to the formula for calculating descent rate. Here is the basic formula for determining the descent rate of a parachute. As you can see from this formula, V is what we're trying to find, which is the velocity of the parachute. M is the mass of the rocket plus the parachute, and it includes the mass of the empty rocket motor. So you have to include that in there as well. G is the acceleration due to gravity. Rho, which is a Greek letter, is the air density, and that is 1.225 kilograms per meter cubed at sea level. And that's going to change based on the altitude, but it's not much. So we can basically use that for our calculations. CD is the coefficient of drag for a parachute. Now this number is a little bit harder to figure out, but for starters, we use 0.75. Now it might be modified based on the type of parachute you're using, the shape of the parachute, and the material that it's made out of. Some nylon parachutes are breathable, which means that you can blow air through them. They're kind of porous. Other parachutes, like the Apogee parachutes that's seen here, which are our nylon ones, are not breathable, which means air does not pass through them. The weave of the fibers is so tight that air doesn't blow through them. So you can actually try to blow air through it and it won't go. It's very tight. But some, like I said, are looser and air will go through them, and that's going to affect the coefficient of drag. It's going to bring that number lower, which means your parachute is going to fall faster. A is the number that we're worried about, and that's our area of the canopy. We're going to use a circular parachute for our demonstrations just because it's easier to calculate. The formula for calculating the area of a circle is pi times the diameter divided by 2, and all of that squared. Now, when you cut a spill hole into it, how does that change this formula? Well, two things are going to change. First, we have the total area. We have to subtract out the hole because it's no longer functioning to slow the rocket down. So this is the big change in the formula. The second change, which might occur, is the coefficient of drag may also be reduced. Now, this is harder to figure out, so we're going to ignore it for now, but you might want to consider this if you do cut out a spill hole. Like I said, it's going to lower the coefficient of drag, so the effect is it's going to make the parachute fall a little bit faster. So again, when we run these formulas, what we're concerned about is the area of the parachute, the outside area, and subtracting out the inside area. And so what happens is I ran some calculations, and these are kind of rough, so don't take them as exact. But so what we're going to do is we're going to cut a circle in the middle of the parachute. We want to know what percentage of the area of the whole parachute that is. So right here on this screen, this hole in the middle is 10% of the total area, which means that the small diameter of this inside circle is 0.316 times the big diameter. So it's a fraction of the big diameter. So as a kind of a reference, this parachute shows a 25% area. So, you know, the small circle in the middle is 25% of the entire canopy area. So when you run the equations, if you look at a 10% spill hole as a percentage of the total area, its velocity coming down is going to increase by 5.4%. So that's not a lot. At 20%, it's 11.8%. 30%, you get a 19.5% increase in velocity. And when you get to 50%, which means it's like you're losing half of the area of the parachute, you're going to be at 41.4% increase in speed. If you want an increase in speed, you want a big hole. But the downside of that is when you get around 35%, it becomes hard for the parachute to inflate easily because so much air is going through the inside that the outside doesn't catch enough to inflate fully. Now, it is possible to do this. They have a special name when it's a very large percent, greater than 50%, and those are called ring parachutes. And if you want to know more about those, we do have an article in our newsletter section on our website that talks about ring parachutes and how to build them. Basically, you have to run the canopy lines across the middle to kind of contain it so that it will open easily. Here I've got a parachute, which I've done that. I just wanted to show you what that kind of looks like. The shroud lines go across the middle of the canopy, and this helps stabilize the parachute. So if you wanted to take a plastic parachute and make it stronger, run the lines across the top, and that will increase the strength. If you want to figure out how fast your rocket's going to fall, we actually recommend using our Roxim software. One of the beautiful things about Roxim is that it already has the spill hole calculations built into it. So what you'll do to find this is to go to the Design Components tab, come down and find your parachute, open that up by double-clicking it, and you'll see the parameters over here on this side. So you'll see the outer diameter, and right now we're set to 18 inches, and then below that is a spill hole diameter. And what it does at the same time, it will also calculate the rate of descent based on the current weight of the rocket. So right now I don't have a rocket engine in it. So let me go back and install a rocket motor. Okay, so now we have the rocket motor loaded down here, which you can see. Then we'll go back to the parachute, open that up, and you'll see it has a calculated mass. Now this calculated mass is the mass that Roxim thinks the rocket will be at when the parachute deploys, which means that there's no propellant in the rocket motor. So you'll see this calculated mass here is different from this mass right down here where it says selected stage mass. The difference between those two is the amount of propellant in the rocket motor. So Roxim is already figuring out that for you, so you don't have to worry about it. And then what you want to look at is the descent rate right here. So right now we're at 12.22, and if I take out the spill hole and make that 0 and hit tab, you'll see that the number changes. So now it's falling slower. And that's the beauty of Roxim, is that you can automatically calculate what the descent rate will be once you create a spill hole in your parachute. Okay, so here is a rocket, and this orange box in the middle is our parachute. And I've ran a couple of simulations, and the first one was with no spill hole. So we launched the rocket and had a total flight time of about 100 seconds. This parachute was an 18-inch diameter parachute, and the spill hole was 3 inches in diameter. And then the flight time reduced because the rocket fell faster, and it was down at 99 seconds. So I wanted to show you a video of what this would look like. And this is from our Roxim Pro software. Let me bring this up. Okay, so down here where my cursor is where the rocket is going to be launched from. This is like in a nice three-dimensional scene right here. And you can see the rocket taking off. And what you're seeing is actually two rockets launching at the same time. Since the spill hole is so small, They don't start diverging the flights until about this point here. And now you can see that one rocket is going to land just a little bit closer or a little bit faster than the other one. We're just zooming in on it here just so we can see the parachutes coming down. You can see one is lower in the sky than the other, and it's not much. Like I said, the big advantage of the spill hole is that it stabilizes the chute. If you want to fall faster, it's probably better to use a smaller parachute. Another option that people often do is they'll take the shroud lines on the parachute. So we got the shroud lines here. You'll put a piece of tape like somewhere in the middle, and what that does is it prevents the parachute from opening fully. This is called reefing the parachute. Could be a simple way to do it on the field, particularly if you have a nice nylon cloth parachute like this one here. You don't typically want to cut a hole in a nylon parachute because they're a little bit more expensive and they're nicer. So reefing that parachute with a piece of tape could be one way to reduce the area so that your rocket falls faster. And if you do want to cut a hole in a nylon parachute, what I recommend is to take your hobby knife and take a heat source, like a little butane lighter, heat up the blade so it's nice and hot. And when you cut into the nylon, it's actually going to melt the nylon cloth because nylon actually is plastic material. And as you know, plastic melts. And so as you're moving your knife around, it's actually, instead of cutting it, it's actually melting it. And that's actually good because what it does is all those fibers around the edge are all getting melted together, and that's going to increase the parachute so it doesn't tend to rip. So if you want to learn more about parachutes and spill holes, we've had several newsletters here at our website that have talked about parachutes and how to make things fall slower or faster. And if you're not a subscriber, go ahead and do that. It's free, and the information is going to be invaluable to you, and it's going to give you access to all of our previous newsletters so that you can view those and find out more information. My name is Tim Van Milligan, and this is the Apogee Rocketry Workshop. May the winds be light, may the skies be blue, may all your rockets fly straight and true.